Write the expression as a decimal and as a percent. If we cross multiply and divide, 6 times 100 divided by 40 is 15%, which can be written as 0.15 in decimal form. Your teacher has a bag with 10 yellow, 10 green, 10 blue, and 10 red cubes. Your teacher conducts a chance experiment by mixing up the cubes in the bag and randomly pulling a cube with replacement 20 times. What portion of the cubes are yellow? Write your answer as both a fraction and a decimal. So there are 10 yellow, but there are 10, 20, 30, 40 cubes in the bag. So as a fraction, we have 10 out of 40. But as a decimal, if we divide 10 by 40, that gives us 0.25. What portion of the cubes are green? Again, 10 out of the 40 cubes altogether. What portion are blue? 10 out of 40. And what portion are red? Also 10 out of 40, which is 0.25. Do you think each color of cube is equally likely to be pulled? Explain. Well, yes, because each color has the same amount of cubes. How many cubes of each color do you think your teacher will pull? Explain your prediction. Well, she's going to pull 20, and there are 4 different colors. Complete the table by recording the first letter of the color of each cube that your teacher randomly pulls from the bag. We are going to record the frequencies of each color. So to start with red, we had 1, 2, 3 red pooled. There were 1, 2, 3, 4, 5, 6, 7 yellows. I see 1, 2, 3, 4 greens. And 1, 2, 3, 4, 5, 6 blues for a total of 20 because we were supposed to pull 20 from the bag. For the relative frequencies, we're doing 3 out of 20, 7 out of 20, 4 out of 20, 6 out of 20, and 20 out of 20. What do the relative frequencies in the table represent? These represent the experimental probability of pulling each color. A chance experiment consists of flipping a nickel and a penny. The first step in finding the theoretical probability of events in a chance experiment is to list the sample space. For this chance experiment, complete the sample space by listing all possible outcomes when flipping a nickel and a penny. Use H for heads and T for tails. Well, I could flip a head on both. I could flip a tail on both. I could flip a head and a tail, or I could flip a tail and a head. So there are 4 different outcomes, creating our sample space: HH, TT, HT, and TH. What is the theoretical probability of both coins landing tails up? Well, TT happened 1 out of the 4 possible outcomes. What is the theoretical probability of exactly 1 coin landing heads up? There were 2 out of the 4 that had only 1 head. What is the theoretical probability of the nickel landing heads up? That is also 2 out of 4. We had head, head, and head on the nickel and tails on the penny. If you flipped both coins 12 times, how many times would you expect the coins to both land tails up? Well, tails up happened, T happened 1 out of the 4 times. But if we wanted to do that experiment 12 times, that would mean that 3 of them, because we're creating an equivalent fraction, if you flipped both coins 12 times, how many times would you expect exactly 1 coin to land heads up? That happened 2 out of the 4 outcomes. So if we're changing that to 12, that would be 6. Consider a chance experiment of rolling a fair six-sided die. How many outcomes are in the sample space of this chance experiment? There are 6 possible outcomes. You can roll a 1, 2, 3, 4, 5, or 6. Is each equally likely? Yes. Each face on the die is the same size. Complete the table listing the possible outcomes for this chance experiment and the theoretical probability for each outcome. Well, we could roll a 1, 2, 3, 4, 5, or 6. So the theoretical probability would be 1 out of 6 because there's one face that has a 1 on it out of the 6. What is the theoretical probability of rolling an odd number? Well, there are 3 odds out of the 6. 1, 3, and 5 are odd out of the 6 possibilities. What is the theoretical probability of rolling a number less than 5? 1, 2, 3, and 4 are all less than 5. So that is 4 out of the 6 possible outcomes. What is the theoretical probability of rolling a number greater than 7? 0 out of 6. There are no numbers. Bigger than 7. The following spinner has 4 equal regions, numbered 1 through 4. To play the game, a student spins the spinner twice and adds the 2 numbers that the spinner lands on. If the sum is greater than or equal to 5, the student wins a prize. In the following table, describe the sample space by listing the possible outcomes of the game. Underneath each outcome, list the sum of the 2 spins. So we could roll a 1 and a 1, which gives us a sum of 2. We could roll it or spin a 2 and a 1, which gives us a sum of 3. A 3 and a 1 for a sum of 4, or a 4 and a 1 for a sum of 5. We could roll a 2 and a 1 for a sum of 3, a 2 and a 2 for a sum of 4, a 3 and a 2 for a sum of 5, a 4 and a 2 for a sum of 6. We could roll a 1 and a 3 for a sum of 4, a 2 and a 3 for a sum of 5, a 3 and a 3 with a sum of 6, or a 4 and a 3 with a sum of 7. 1 and 4 for a total of 5, 2 and 4 for a total of 6, 3 and 4 for a total of 7, and 4 and 4 for a total of 8. How many outcomes are in the sample space for this chance experiment? There are 16 possible outcomes for this chance experiment. And it says, is each outcome equally likely? Well, yes, because each piece on the spinner is the same size. So what is the theoretical probability of each outcome in the sample space? That would be 1 out of 16. What is the sum of all theoretical probabilities of all the outcomes? Well, there are 16 out of 16, which is a sum of 1. Then it says complete the probability model by using the table from part A. Record a theoretical probability for each sum of the chance experiment. So the sum of 2 only showed up once out of 16, but 3 showed up twice. 4 occurred 3 times. 5 occurred 4 times. 6 occurred 3 times. 7 showed up twice. And 8 only occurred once when we had a 4 and a 4 spun. To win the game, the sum of the 2 spins must be 5 or greater. What is the theoretical probability of winning the game? Well, 5 or greater would be all of these possible sums. So we have 4/16, 3/16, 2/16, and 1/16 all combined. They have the same denominator, so 4 plus 3 is 7, 8, 9, 10 out of 16. Because 10 of the possible outcomes had a sum of 5 or more. A game requires spinning the following 2 spinners. A person wins the game if both spinners land on the same color. Dylan says there is a 50% chance of winning the game because one spinner is completely red or blue and half of the other spinner is red or blue. Explain why Dylan is incorrect. Well, we could land on red and red. We could land on red and blue, red and green, or red and yellow. We could also land on blue, then red, blue, then blue, blue, then green, and blue, then yellow. So for them to land on the same color, that occurred 2 times out of the 8 possible options. That's not 50%. 2 out of 8, which is 0.25 or 25%. There were only 2 out of the 8 possible outcomes where they land on the same color. That is a glimpse at theoretical probability, what we would expect to happen in comparison to our experimental probability like we saw in the previous lesson.